So today is the lecture. So recording wise, today is 35th video lecture, which is going to be recorded. Other than all this assignment exam. By the way, Anvesh, if you want to give your assignment exam, you can talk to Mohammed Roshan. He will tell you what to do. Okay. Assignment 2 exam, right? For you, assignment 4 exam. Only two are there. Who had some problem with medical, right? So anyway, so there are various filters which we are studying right now. If you want to call someone, like some of the friends who are not here, you can call them. At the end, we will have surprise quiz. Still, like your 3 lectures are left, so we can have it. Anyway, so we understand what is filter and what's the role of various filters. Right? Uh, but all the low pass filter transfer functions are not unique one when you are increasing the order. When I'm saying the order means you may have something like this. So this is second order, right? This is also second order. What is the difference between these two? Can you see some difference between these two transfer functions? Mahima, can you see? What is the difference between these two transfer functions? Yeah, Aishwarya. What do you think about these two transfer functions? So we have two transfer functions. First one will have two poles at -3 and -1. No, sorry. It's imaginary. Sorry, I thought it's 3s plus 2. Right? Here also, like, you will have similar thing. Right? In both the cases, you have two poles. Both are imaginary. Complex and conjugate pairs are there. Both are second order. But which one are you going to prefer? You can prefer any one of them, depending on your application, because application will tell you that I need following characteristic of I may have this kind of low pass filter where there are three different zones. This is known as pass band, this is known as stop band, this is known as roll off, right? So roll off is depending on the order of the system. If this is -40 dB per decade, you have to take second order. If it is -60 dB per decade, you have to take third order, right? And there are two frequencies. One is F1 and second is F2. F1 is the frequency after which this passband is getting over and the roll off starts. Similar for F2 is stop band frequency from where the stop band starts. So you have roll off between F1 and F2. So these frequency might be given to you. This roll off has been given to you. And other than that, in reality, if you have various roots which might be available on complex conjugate pairs, and you may have some ripple. This might happen. So this ripple is going to be known as passband ripple, and this is going to be known as stop band ripple. So that limit should have been given to you, that how much passband and stopband ripples are allowed, what is the roll off, or it will be given in terms of f1 and f2. And when somebody is asking or writing this statement, design a second order with some word here, filter, then with following specs. So those specs might be passband ripple, stopband ripple, f1, f2 roll off, right? And this word is the word where you are going to have, so you can fill this blank with following words. One is called Butterworth, one is called Chebyshev, and one is called elliptic. So these four are the approximations, or these are the different mathematicians in different era. They came and they gave the technique through which you can find out the transfer function for whatever the system you have to design or for your given specifications. But note that when you are using Butterworth, Butterworth is known as maximally flat response, and its roll off is poor, or you can say that does not have passband and stopband ripples. It will not be there, or you can say that output will look like this one. If you are increasing the order, if you are decreasing the order, right? So in stop band and pass band, so these two region are pass band and stop band. These pass band and stop band won't have any ripple, and this roll off will be depending on the order. If it is second order, it's minus 40 dB per decade. If it is third order, minus 60 dB per decade. And these are the things already known to you, right? As order is increasing, means number of poles are increasing. And for most important thing is, this is the function which is all pole function only. It will have all the poles with some constant value. Means transfer function will look like this. Right? In this case, actually, A will be 1. But if you are writing in terms of s plus omega 0 raised to n, then this will be omega 0 raised to n. Right? Similar transfer function, maybe you have studied in control theory, those who are studying control theory, and if you are going to study next year, then you are going to see same transfer function in control theory, like this one. If it is omega n square, s square plus 2 zeta omega ns plus omega n square, this is second order transfer function where you are going to divide omega n square. So this is also all pole transfer function, may not be Butterworth. So what Butterworth told us, that whenever you have to design a system which is going to have following characteristic, where is it? Yeah. That you want maximally flat response in pass band and stop band. Even though roll off is poor, it's okay, fine. And if you want just all pole function, then use my approximation. And once you have the transfer function is available, let's say this transfer function is available, can you draw the circuit? If this transfer function is given to you, can you draw the circuit using op amp? Yes or no? Akshita, no? Okay. Piyush, yes or no? So you can rewrite this equation as right. And after rearranging all these things, you can find out some equations where you can implement this with double derivative, single derivative. So Akshita, I should suggest you should watch my maybe lectures which are recorded previously, maybe 30th lecture, right, where I have told how to design such system, right? Two differentiator, one differentiator, and you can get the answer, right? And we also studied that if you have to find out the value of R and C, the ratio has to be kept such a way that R has to be very high value just to make sure that it will not load the output, right? And capacitor has to be low, preferably in the range of somewhere microfarad, and this one may be in the range of 100 kilo ohms, right? So you can make the circuit using op amp if you know what is the transfer function. But that transfer function will have three different three different approximation. One is Butterworth, where you will have maximally flat response, roll off, and pass band, stop band ripples will not be there, and the function will be all pole function. However, if you are talking about Chebyshev approximation, that Chebyshev approximation is going to give you this kind of response. Means Chebyshev approximation has been given such a way that their poles and zeros are going to give you some oscillations at pass band and stop band. Either this is magnitude with respect to frequency. And the elliptic function, that's one of the difficult one. We are not going to study, and it's not given in also in book. But it's combination of these two, where you will have lower pass band and stop band ripples, and the roll off is also not very much poor. It's combination of both, right? It will take some good characteristic of Butterworth and good characteristic of Chebyshev and keep it for like next approximation. So that is what we are calling elliptic. However, in reality, people avoid to use this one because mathematically their equations are very complicated and it's not intuitive. So people should not they are not using elliptic. Do you have any problem, Swarna? Okay, please. So while I'm talking, please, if you are making smile, then I don't know. Same for Mahima. Right now you are smiling, right? So if something is going on, please let me know. There is some problem. So in that case, I'm going to solve some equations for Butterworth, that how Butterworth will look like. So Butterworth filter will have following transfer function. So this is the thing which was given by Butterworth. By the way, this is name of the person. That's why we are going to keep Butterworth as like B always in capital, right? And here N is order of the system or the number of poles. Right now, the function is normalized to omega 0, where omega 0 is the center frequency. if you want to relate it, this is the ideal low pass filter which I am expecting, but this is not possible to get. In reality, if you are going to have just second order filter, then what you are going to see, something like this. By the way, if you are equating your magnitude with respect to 1 by root 2, or if your transfer function where have I written? Okay. So if omega is equal to omega 0, by the way, it has to be square root, right? So it's wrong. Just magnitude will give you this one, right? This is correct, right? So at omega is equal to omega 0, what is going to happen? You are going to see h of j omega 0 square equal to 1 by 2, and the magnitude, if it is h of j omega 0, you are going to see 1 by root 2, which is going to give you 0.707, and that is also going to give you minus 3 dB, right? So the frequency where the magnitude response becomes 0.707, that frequency we are going to define it as minus 3 dB, and that is our interest of frequency. Or you can say that the whole transfer function has been normalized to omega 0 raised to 2 raised to n. Whatever the order of your transfer function, or the how many number of poles are there, it doesn't matter. This transfer function at omega equal to omega 0 is become 1 by 2. If it is square, if it is just single value, it's 1 by root 2, right? So it does not depend on the order. So you can redraw that thing. If this is 1 by root 2, this is 1. If it is second order system with minus 40 dB per decade, you are going to see this thing, or at omega 0 this thing will happen. If it is third order, you are going to see something like this, where the slope get improved and it's minus 60 dB per decade. Fourth order will give you minus 80, and as you are increasing, it will be become better and better. However, you are not going to see any ripples over here, so it's always maximally flat, and this point is always omega 0. And remember, we are normalizing whole transfer function at omega 0. That's how we are getting some DC quantity. Otherwise, there is no DC quantity. It's only all pole with omega 0 raised to 2n. That's the DC quantity. Sorry, which one? The first one, yeah, this is j omega 0 square. Sorry? J omega naught. I should have written j omega. It's fine. It was a mistake because of actually most of the books, if you are into analog, and so there are basically filter might be two kinds of filters. One is analog and one is digital. What we are doing right now with op-amp is actually analog filter. Generally all the books, they are following this omega for analog and this omega for digital, but I am following this omega just to make sure that it's same as what written in Behzad-Razavi. So otherwise you should follow this notation for analog filter. So that's why I got confused here, right? So otherwise in book it's written like this. We are following exactly what book is saying. Okay. Now, before moving to all such things, let's have one question. So, there is an illustration where you have to design a low pass filter that must provide you the passband flatness of 0.45 decibel for f less than f1, and for higher than that one you are going to have attenuation of 9 dB, which has been kept pictorially here, right? So you need to determine the order of the Butterworth filter satisfying these requirements. Can you try? So we have only one equation. We have only one equation. So the magnitude of this one at passband is already given to you, right? Magnitude of this one at passband is already given to you. That is actually 0.45 dB, right? So can you convert this 0.45 dB to normal scale? So because other side, if it is not in dB, because if you want to make this one is dB, you have to add 20 log here extra. If you don't add that one here, then you have to convert this to normal scale, right? So what will be the value? 0.45 dB in normal scale. Sorry, 2.8. Look, 2 is equal to 6 dB plus 0.8. So this will be 2.8 is equal to around 8 dB, by the way, right? You are making some mistake. Look, if you are seeing something in fraction, it's 0.06. Is it correct? Or let me check what. It should be 0.95 square. 0.95. And its attenuation is 9 dB. So you have to reduce this 0.995 by 9 dB and you should get the answer. Anyway, so these are the, this is for passband frequency and this is for stop band frequency. By the way, both the frequencies are getting normalized at omega 0. This is going to be given by specification that you want low pass filter for so much frequency, right? If you remember, this is a frequency after which you don't want any signal. So this is also known as center frequency or the cutoff frequency or the 3 dB frequency, right? After which you don't want a signal, or the signal will be attenuated by minus 20 dB per decade in the case of first order, in the case of second order minus 40 and so on, right? So after getting these two, you can find out omega 0 in terms of f1, and by taking the ratio of these two you can have this one. By the way, f1 and f2 both the values are already given to you, which are in octave. You can see it's 1 megahertz and 2 megahertz. So this is in octave. We understand what is octave, right? Do you understand what is octave, by the way, Akshat? Octave is double, right? So f1 by f2 ratio is already given to you, which is double, and you can solve it and you can find out n is equal to some value which is coming less than 3, but you can round it off to 3. You will not get exact answer of, like, you may get something 2 point something. Can you solve it and just let me know what is the exact answer? By solving this equation, can you tell me what is the n? Already I wrote something, but you will not get exact n equal to 3, right? You will get some other number. Yes, Akshita. Gaurav, you are early for the next lecture, right? So f2 by f1 is 2, by the way. 2 raised to 2n is equal to 64.2. How to solve such thing? 2.98. So n is equal to 2.98. So you have to round it off and you can get this number. So such kind of things can be asked to you. F1 and F2 are already given to you. And for n equal to 3, when I am going to plot the response, what I am going to see at roll off, it will be minus 60 dB per decade, and this will be 1, right? This is what I am going to see. Yes? Should I go ahead, or are you following this till now? So Butterworth has given only one thing. He told you have to follow this equation, because this equation is going to give you maximally flat response at pass band and stop band.
P value should be greater than 3 because at that 2 to the power 6 we get 64. So it is 64.2.
N is equal to how much you got? Is it 2 point?
3.001.
3.0001. Okay. So then you can like make it n equal to 3, or you can make it n equal to 4. Right? Depending on what do you want to design something tight specification, then you can go with like 3, or if you want to make it over design, you can go for 4. But increasing order, you need like almost one extra stage, which will have capacitor or inductor or something will be there. So it is always creating lots of problem. Capacitor invites all the noise because it will allow small fluctuations. It will detect it and it will add in your signal, right? So if you have less number of order, then it's good generally in terms of noise. Otherwise on paper you can do anything, right? Anyway, so if you know that HA, because I'm writing analog filter, omega square is equal to 1 by omega 0 raised to 2n. Do you know that the fact that HA j omega square is actually combination of two things? Do you know or not? Do you know what I can write down? Equivalent of that. What is that? Conjugate of j omega, right? This is the symbol of conjugate, right? Okay, then it's good. Yeah, mod is not required in that case. Yes, you're right. So that is equal to 1 by omega 0 to n, and I can write down this as HAS times HA minus S is equal to 1 by 1 plus minus S divided by omega 0 raised to n. Hmm. What? Hmm. You are going down by 9 dB. You're going down by 9 dB. This band is like, this point is available at 0.45, and this point you have to go down by 9 dB. And for going down 9 dB, how much value you are going to see here? Note that everything is in decibel. Log, you need to convert it to linear scale. This is log scale actually.
It is 1.057.
You check all these numbers because we don't have much time, so that we cannot discuss on that right now. Okay, so I'll check that and I'll let you know, right? So that question is already solved in your Bezer Razavi book, so you can check that. Maybe some mistake is there, right? Anyway, so here you can write down this. So can you tell me where the locations of poles? For such system, can you solve this? You must have studied in mathematics somewhere in your 12th standard trigonometry. How do you solve this? You can substitute this one as -1 is equal to -1. And what can you write down for -1? Do you remember or not? Where k equal to 1 to n, not 0. Yeah? Do you remember this equation? If you forgot, please write down in your notebook. If you are interested in filter design or DSP, you have to use such equations every day. Okay, if you forgot, you can write down, right? So can you write down now this equation in terms of sine and cos? Write down in your notebook. So we can write down this minus s by omega 0 square raised to n equal to -1 is equal to e raised to j2k minus 1 pi, and this k is going from 1 to n. I can take this n that side, which can give me sorry, this has to be a square. Right? Till now, is there any problem? I can do this thing also, that s square is equal to minus omega 0 square e raised to j2k minus 1 pi by n. Right? Now I'm interested in finding out the pole location. So let's call this one as sk. These are the number of poles, by the way. K denotes the number of poles. So this is going to give me omega 0. Sorry. This is going to give me plus or minus j omega 0. And this is going to give me 2a. Right? So I'm taking the square root of the entire thing. So this is going to give me this one, and this is going to give me this one, right? If you are getting any difficulty, please let me know. You can stop there. Sorry? K is number of poles. Yeah. So now I need to keep k is equal to 1 to n. If I'm going to keep that, then I can find out. Look, other way around, you can write down in terms of real part and imaginary part. Right now, whatever we are doing, it's in complex number. If you remember, a plus jb can be written as if it is real, imaginary, you know the angle. So I'm writing in terms of angle. Right now it will be angle, which will have two components. One is sine and one is cos. Right? So can you write down this in terms of sine and cos? Yeah. So what is that? Cos 2k minus 1 pi by 2n, then plus j sine 2k minus 1 pi by 2n. Yeah. Now I can take this j inside so that things will be easier for me, where this is become minus sine 2k minus 1 pi by 2n plus j cos 2k minus 1 pi by 2n. All correct? Or if you are making mistake, just let me know. Sometimes I make mistake here. Sorry? one positive and one negative. Where is one positive? So there are two things are already given to you, right? Plus and minus.
There will be 2k number of
2k number of no.
total.
Yeah, total will be like, if you are in this equation, you will have 2k number of things, because everything is uh, look, the equation where you are getting the answers, those are complex and conjugate pairs, by the way. So definitely you will have to. So that's already known fact. Depending on the order, right? If you have x n plus something, so you will have n roots. So that is what we are finding out here. In this case, maybe 2 raised to n. Yeah. So tell me, what is so this equation you can write down somewhere. So that equation says that this equation is correct, right? There is no error, right? Okay. If there is no error, there is one more thing. We are going to talk about only positive real function. We are not going to take all the poles which are available at right half plane. We are not going to synthesize them. So we are going to only talk about this plus sign, not minus. We are going to drop that because that's not the one which we want. We want only these roots because they are the positive real function. They are available at negative side.
Our roots are always in pair.
Yes, so you will have pair.
So then k represents a number of poles. So
K.
so k should be only
K actually n is I should okay. Yeah. So what you are saying, you are correct.
saying that
K is number of poles. Yes,
so
correct.
k should be even multiple of should be even.
It may be odd also. It may be odd. It may be odd. You may maybe you are designing third order system, or fifth order, or seventh order, or ninth order. Then one of the pole will be real. We will see that. Let's assume that you are designing n equal to 1. So I'm going to give you, let's say, one question that you have to design a first order Butterworth filter with different specifications are there, but before that I need to find out the transfer function. So transfer function will look like this one. Let's call this one C, right? So I need to find out sk0. So you can keep the values where k equal to 1, right? It goes till n is 1 here. So order of the system is 1. So you are going to see minus sign pi by 2 plus j cos again pi by 2. Can you tell me what will be the answer in that case? How much you got? Minus 1. Right? So that's a, yeah, sorry, it's normalized to, right? So if it is first order, you are going to see pole at omega 0. It's a real value, by the way. Right now it's not complex. But if it is n equal to 2, now can you tell me what will be the locations? Hmm.
So why did we remove that minus omega part?
Minus, we don't want any unstable system. We need stability.
Root should not be on right.
Yeah.
So but the sign 2k minus 1 pi by 2 can also be negative at some point of time. So if there is a minus omega factor, then it can
If it is coming minus, look. So there are two possibilities. What you are saying, you can go here or here. but still you are staying in left out side. This is negative number, by the way, right? So this can happen. You are right. You are going up or down. You are not going right or left.
For the sine factor, the sine 2k minus 1 factor, that is
Yeah, so sine is available vertical line. No?
so that a
Let's do one thing. Let's find out what is happening at n equal to 2. Then I'm going to solve it for n equal to 3 also, and then we'll see. Right? So what is happened? If n equal to 2, you have to keep k equal to 1 and 2. And you have to find out. Minus, okay, so it's exactly coming what? Yeah. And j times omega 0 by root 2. Huh? This is plus or minus, right? Yeah. Right? So you are going to see something like this. Right? Now, can we solve for n equal to 3? So now one of the root will be real. Two roots will be complex and conjugate. Right? Yes. Desraj, are you following or? So one of the root will be omega 0. Is it omega 0? One of the root is omega 0. Right? Yeah, minus. Sorry. My mistake. I should have called. So what are the angles? Yeah. So if you're looking at here, when k equal to 1, your angle is pi by 2n. Right? So each value of pole, or let's redraw this, if it is not normalized to omega 0, then you are going to see the circle. You must have studied in school where unit circle, but now that unit circle will be changed to omega 0. And all the poles must be lying on this circle only. And you have to find out what angle you are going to see. So if k is equal to 1, the first one will have the angle of pi by 2n, right? And each pole or each pole value are apart from each other by pi by 2n. So you may have many. So this angle will be pi by 2n, the difference. So as you are increasing the order, if it is odd number of entries, then one of the pole is equal to omega 0, right? So if odd entries are there, then one of the pole is equal to omega 0 minus omega 0, right? And if all the even are apart from each other by pi by 2n, if you are keeping that, you will get the answer, right? In the case of third order, you will get 60 degree, right? The difference of 60 degree, because from here to here it's 180 degree, right? With real and imaginary thing, you can find out where they are lying, right? So if you are keeping your poles on this unit circle, if it is normalized with the center frequency, then that approximation is Butterworth approximation, and that is going to give you maximally flat response. This is what Butterworth has told. So Butterworth has told that, so there are two possible things. If you are drawing the low pass filter for magnitude with respect to frequency, you are expecting something like this, right? But there may be the case that you will get this answer also. This is all depending on where you are keeping your pole and 0. So Butterworth told that if you want to see the blue kind of curve where it's maximally flat, such kind of thing are only possible if you are keeping your poles kept on unit circle. This is what I was saying, right? And this we already proved it from the equations. And from this we found out that the equation will be like this, right? So through that you can write down all the different equations. So if it is third order, you should be seeing, I'm just what I solved. Okay, n equal to 3, I got omega 0 1, s1 equal to minus 1, s2 and 3 are equal to minus 1 by 2 plus or minus j root 3 by 2. Are you getting same answer for n equal to 3? Okay, means my calculations are correct. Similarly, you can try for fourth order, fifth order, sixth order, seventh order, right? And you can find out the transfer function. Butterworth transfer function will look like as follows, right? So if you stick to this one, you will get the answer at certain place. So let's assume that you are designing third order filter. Let's write down the transfer function. How does it look like? So transfer function in this case will look like this one: s plus 1, s plus 1 by 2 plus or minus j root 3. This is correct, right? So you're going to get this kind of output, but this DC component will change. If you're writing in this way, then DC component will be I guess you can understand how I have written this, right? So using this equation, you are going to get something like, so I'm writing some general equation which I found out. So this is the generalized equation for third order system, right? So now can you draw the circuit using op amp, because that might be the last answer, right? And can you scale them with omega 0 value? Let's assume that omega 0 is equal to 1. So now can you design a circuit using op amp? Sorry? Yeah, SQ. It has to be SQ, otherwise this will not work. Thank you. So by the way, transfer function is VO by V in. So V in is equal to VO S cube plus VO times 2S square plus VO times 2S plus VO. You can write down in the other way around also. VO in terms of V in is also possible. Right? Then you have to find out partial fraction method. Through that you need integrators. So the solution of this transfer function may not be unique, by the way. The solution of this transfer function may not be unique. You can go via, so here you can see it's, you can, through partial fraction you can find out the things, right? So there also you will have different answer. Yes, Swarna. So you got the answer. Can you draw on board? So, yeah, you have to draw on board. Yeah, you can practice here, Swarna. Now I can laugh.